Okay, hello everyone. And this is the first WiNS seminar of the fall 2025 edition. And the first speaker is Yanna Kraakman from University of Twente in the Netherlands. And she's gonna talk about sampling random hypergraphs with fixed degrees. And yeah, you have some time for the talk, and then in the end there will be time for questions. And thanks for presenting today to us. I leave the floor to you.
All right. Thank you for the introduction. Yeah, thank you for inviting me. I'm very happy to give today's talk. Yeah, so I'm going to talk about random hypergraphs with fixed degrees and how to sample those. But before I do so, I'll quickly introduce myself. I wanted to share with you a cool picture that I took last summer. I went on holiday to Scotland and we saw this amazing cliff when we were on the boat towards the Orkney Islands. It was a very beautiful view. There were some cool seabirds around there as well. And I guess this is a very different view than we get in the Netherlands because we have a very flat country, right? So I guess this is why this was very spectacular to me. So yeah, I'm from the University of Twente. You may have seen this picture or maybe not. We have this drowned tower in a pond, which is our main attraction, I would say, with a very beautiful campus as well. And I'm a PhD student. I'm in my final year now, and I'm being supervised by Clara Steeghuis and Albert Wong. Clara is also in network science. Albert is in chemical engineering. All right. So let's go into the contents of my talk. I will start by introducing hypergraphs. Then I'll talk about why we want to sample them randomly. I'll introduce two algorithms to do so, and then we will compare the speed of these two algorithms. All right, so let's start with the hypergraphs. Hypergraphs are a generalization of graphs. So I'm going to first show a picture of a normal graph in which each edge is a set of two nodes. And in the hypergraph version, each edge can be of any size. So here we see the orange edge of size 3 here as well. And then we can also have edges of size 2, like the regular edges. There's also a directed version, which is mostly the content of my work. So let's first look at the directed graph. Here, every edge has one tail and one head node. And in the hypergraph version, we can have a number of tail nodes and a number of head nodes. So here in the orange edge, we have two tail nodes, A and C, and we have one head node, B. And again, we can also have a normal directed edge here as well. Now, these directed hypergraphs are a very convenient way to model, for example, chemical reactions. So let's look at such a chemical reaction. So this is one that you may have learned in high school. Hydrogen and oxygen combine to become water. And this you can model very easily with a directed hypergraph in two ways. This is one of them. So we have the node 2 hydrogen, node oxygen, and we have the node 2 water. And then this is the hyperedge that I'm showing here. So I guess this is the easiest way to model this reaction. We have these coefficients within the nodes, which may be a bit odd. So a different way is to take those coefficients out of the nodes and into the edge instead, right? So here the hydrogen appears still twice. You can see that because it has two connections to the edge, and you can also see it here twice in the edge. And the same with the water. And such hyperedges with these double connections inside, we call those degenerate hyperedges. Right, so my PhD is about sampling or about analyzing chemical reactions like this, but then a whole bunch of them that are somehow connected together. So this is the full system of reactions that I'm studying. So every one of these hyperedges is a chemical reaction. There are 16 of them here, I believe. And we have a bunch of different molecules involved as well. And in studying such systems, we can observe a lot of different characteristics. For example, there seems to be some kind of cluster here. This trypsin or the TR molecule seems to be somewhat central. And we can see reaction R4 going one way and R5 going back. So these are all kind of observations that we can do. Another question is which of these properties are actually telling us something about the underlying mechanism of our system, and which of these properties are actually due to randomness. And this is a question that not only us, but many network scientists ask. And you can try to answer that by comparing your specific system to a randomized version of your system. And this is what we call the null model. So we are comparing our specific system to a random version, which has the same nodes, and the nodes have the same degree as well. So for example, this node down here still has out degree 2 and in degree 1, same as on the left side. With the same number of edges, hyperedges as well. But the specific way that the hyperedges connect to the nodes, this is what we randomize. All right. And then we're going to compare the properties of both of these hyperedges. Okay, so this is the first takeaway of my talk. We need to have a randomized version or a null model of our hypergraph in order to find these non-trivial properties of my specific system. All right, now we're gonna look a bit more into more detail what it means to sample such a hypergraph uniformly at random. So we want to sample a hypergraph with fixed degrees. We're going to do that uniformly. So let's first look at the fixed degrees. What does that mean? Well, we're going to use a small example for that. I'm going to just fix some degrees, right? So now I pick 5 nodes. 3 of those have degree 1, 2 of them have degree 2. From here on, most of my talk is going to be about undirected hypergraphs because it's a bit less technical than the directed version, but everything also applies to the directed version as well. And in the very end, I will get back to the directed version. All right, so for now, undirected, 3 nodes with degree 1, 2 with degree 2. And also the edges have degrees now because the edges can have specific sizes, right? Not just size 2. So I pick 2 edges of size 2 and 1 edge of size 3. And now I'm interested in sampling hypergraphs with those specific degrees. So one specific hypergraph that has those degrees is this one. We see node A, B, and C are all in one. They all participate in one hyperedge, so they have degree 1. And D and E appear in 2 hyperedges, so they have degree 2, as we need. And the edges, we see 1 orange edge of size 3, and we have 2 edges of size 2. And down here, you also have the set notation. All right, so this is one example, but there are others. This is another one. And this one as well. This one is a bit funny because the orange edge is supposed to have 3 nodes, which it does, because node D is in there twice. It's a bit awkward to draw, but down there in set notations, you can see it better. Sorry. All right. Okay, cool. So this orange edge is a bit weird. And again, this is what we call the degenerate hyperedge. Okay. So for the sake of simplicity, I'm going to try and sample hypergraphs with those degrees without degenerate hyperedges. This is also something that happens a lot in practice, that you don't want such degenerate hyperedges. Okay, so how many of these hypergraphs do we have with those degrees? It's 16. These are the 16. All right. I'm going to put them in a circle. These are the same 16 that we already had. And now we want to sample one of these uniformly at random. And this is not so difficult because you can just throw a oh, you can just throw a 16-sided die and then pick the hypergraph that corresponds to the number that you get. But in practice, we are interested in very big systems, and you don't know beforehand how many hypergraphs have the specific degrees that you're looking at. Also, if you don't want degenerate hyperedges, it becomes more difficult as well. So keep in mind that I now show the full picture of all these hypergraphs, but usually we don't know how many we have. Right. So I'm going to present the first algorithm to generate one of these uniformly at random. It's called the hypershuffle algorithm. And to use it, we need to have at least one of these to start with, which we call the initial sample. Let's say it's this one. And usually we do have at least one of them that we can use as an initial sample. For example, I just showed you the chemical hypergraph that I'm working with. And in that case, that's the first initial sample that I can use. Right, so we have our initial sample, and now we're going to loop through these 3 steps many, many times. That's the algorithm. Right, so we're going to start with picking 2 hyper edges at random. I picked the orange and the green one now. Now I'm going to take the union of the 2, and now we're going to randomly repartition them again into 2 sets, for example, like this. And in doing so, we make sure that the sizes of these hyper edges stay the same, right? So the degrees of the edges, they remain the same. Okay, and now we can apply these new edges to the hypergraph. So we remove the old ones and we add the new ones, and we get this one. You can check that it's correct because the blue hyper edge hasn't changed, which is good because we didn't pick it. And the orange and the green one have changed. Okay, and now we obtain this new hyper edge, which is going to be our new state, or this new hypergraph. This one, it's here on the circle. Sorry. Okay, now we do it again. We pick 2 hyper edges, for example, these 2. We take the union, and then we repartition again. And we apply those new edges as well. Here you can see that the orange edge hasn't changed. Okay, one more example. We pick 2 edges, we take the union, and we repartition. And now you can see this is possible because everything happens at random. It's possible that we obtain edges like this, which are degenerate hyper edges. This one is degenerate because it has D twice, and this one is also degenerate because it has E twice. And we don't want that in this specific setting, so we don't accept this specific step. And instead of applying the new hyper edges, we just stick to the same hypergraph that we already had. All right, so if you looked at the circle here, you've seen that we were hopping through different states. And if we now look at all possible different transitions that we could have made, it looks like this. Every one of these lines is a possible transition in both ways, both directions. And we also see these little loops here at the end. The endpoints, these are self-transitions. So from any of these hypergraphs, you can always transition back to the same hypergraph as well. And this describes the Markov chain, which is underlying this algorithm. And so the algorithm is to just hop this Markov chain many, many times. And then the goal of the algorithm is to then end up uniformly at random somewhere along this circle of hypergraphs. And to translate that into Markov chain language, if you do many transitions in your Markov chain, at some point you will end up at the stationary distribution of your Markov chain, which tells you with what probability you are in any of the states. And if this stationary distribution is uniform, it means that we are anywhere on this circle with the same probability. And this is exactly what we want to achieve. So we want our Markov chain to have a uniform stationary distribution. And that's the case if these three properties hold. So the Markov chain needs to be doubly stochastic, which is some kind of regularity condition on the nodes or on the states. This is easy to show that it's true. It needs to be aperiodic, which is also true because there are these self transitions. I won't go into too much detail there. And it needs to be irreducible, meaning that wherever we start on the Markov chain, we can reach any other state as well. This is a very interesting property. It's quite difficult to show as well in general. But we were able to show that for this specific algorithm, that the Markov chain indeed has a uniform stationary distribution. So that's for the case that we don't allow the degenerate hyperedges to be there. And this is a very general result. It doesn't depend on the degrees that you picked in the beginning. So independent of your initial system, this algorithm will come up with a uniformly random picked sample. We also have a different result for the case that you do allow degenerate hyperedges there, then still the algorithm will work independently of your initially picked degrees. All right, so this is the first algorithm that I wanted to show. I'm now going to go into a second algorithm, which is very similar. It also has an underlying Markov chain, which we will get to in a bit. But there are some small differences that I will point out. We call it the hypercurveball algorithm. It's based on the curveball algorithm for graphs, but we generalize it for hypergraphs. We have the same setup, so we need an initial sample again. Let's take the same as before. And now we're going to loop through these 4 steps. And they're the same as for the other algorithm, but the things in cursive are different. So instead of picking 2 random hyperedges, we're now picking 2 random nodes. I pick A and C. And I'm going to look at their incidence sets. So that those are the sets of edges that they participate in. So A participates in the orange edge and C participates in the blue edge. Now we're going to take the union of these incidence sets and then we're going to randomly repartition them again. And then we're going to apply these new incidences. And it looks like this. This is a bit more difficult to grasp first time. So let's check if it makes sense. For example, node B, we did not choose node B. It was in the orange edge and it still is in the orange edge. So it didn't change its incidences. But A changed from the orange to the blue edge, which is also exactly what you can see here. Okay, so we have obtained this hypergraph. Let's do it again. I pick 2 nodes. We take the union and we repartition. And also here, if the 2 sets are of different size, we make sure that they have the same size as in the beginning after the repartitioning. And we might obtain this one. And a third example is this can always happen. So we repartition them, and since everything is random, they can be repartitioned in the exact same way as they were before. And in this case, then nothing happens as well. This is also this self-transition that you saw before. Okay, so this is a different algorithm, but it's still Markov. It can still be described by a Markov chain. It looks like this. It's slightly different than the other one. I don't know if you can tell. We will compare them in a second. But still, these 3 properties need to hold for this algorithm to give us a uniform sample. And we were able to prove that this is indeed the case, where if we don't allow degenerate hyperedges, and also if we do allow for degenerate hyperedges. And again, this is independent of the degrees that you pick in the beginning. All right, so this is the second takeaway. I presented two algorithms. The first one mixes the hyperedges, and the second one mixes the node incidence sets. And they're both described by Markov chains. These are the two Markov chains. Here you can tell that they're really different. The left one has more connections at the top. The right one has a bit more uniformly spread. And if you pay close attention, you've noticed that I've been talking about performing like many, many steps of the algorithm. Like in theory, we perform infinitely many steps, but obviously in practice, at some point you need to stop your algorithm. You need to be happy with the result. And we can only stop the algorithm if we have approximately reached the stationary distribution, or if we have approximately obtained a uniform sample. Otherwise, the algorithm didn't do what it's supposed to do. And this is what we call, in Markov chain terms, we call it the mixing time. So how many steps of the Markov chain do you need to perform in order to approximately reach the stationary distribution? That's the question. And this is actually different for these two algorithms. So you can take a little moment for yourself to think about which of these two do you think is going to be faster to mix. Obviously, you don't have all the information because there are probabilities involved here as well. Every transition has a specific probability, which you don't see, but still maybe you have an idea of which one you would think is faster. All right. We're now going to look at an experiment, and then we're going to see which one is actually the fastest. Okay, so how do we experimentally verify this? Well, I'm going to perform the algorithm many times. I did it 10,000 times here, I believe. On the x-axis, we will see the number of steps that the algorithm performs. And on the y-axis, you see the how much your current sample is different from the initial sample. So in the very beginning, your sample is going to be the same as the initial sample. So you're going to be somewhere down here around 0. And as you perform more steps, your sample is going to be more and more different than the original one. And then you're going to observe some trend like this, where your sample is going to grow more and more different than your initial sample. And at some point, this is going to converge because you can't grow more and more different forever. So it's going to converge to something just below 1 usually. All right, so we did this. Yes. And the point at which it seems to converge, this is where we say that the system has mixed. So this is the number of steps that you need to perform for this specific system then. So we did this experiment for both the hypercurveball and the hyperedge shuffle algorithm. And these are the results. So I did this 10,000 times, and the lines here are the mean results, and the shaded area is the standard deviation. And here you can tell that the orange, so the hypershuffle algorithm, so that's the first algorithm, is way faster than the other one, because this one needs around 6 or 7 steps, whereas the other one needs like 17 steps, right? It's a very small system. So usually you wouldn't find such low numbers, but for now the difference is quite big. So yes, this left Markov chain seemed to be the faster one here. And we did experiments like this as well for real systems, bigger data sets. We found some results which are the opposite of what we just saw. So here the hypercurveball algorithm is faster. The other one hasn't even converted yet after many steps. And we saw systems which are kind of similar to what we just saw. So from this, we learned that depending on your specific situation, one of the two algorithms can be significantly faster than the other. And we were wondering what makes for this difference, or how can we tell maybe without doing all these experiments, which one is going to be the faster algorithm for the specific use case that we have. Right, so for that, I'm going to dive into a tiny bit of theory. It's mostly just to get some intuition of what it means for the system to have reached its mixing time. And from this, we're going to obtain some hypotheses that we can test. Okay. So for the Markov chain to have reached its mixing time, it means that the current sample that we have is not biased by the initial sample that we had. That's the first observation. And for this to be the case, it must be that kind of every part of the initial sample must have changed somewhere along the way during this, like along the way of the algorithm. Because if we have only performed 2 steps of the algorithm, for example, maybe the initial sample didn't even have the opportunity to fully change, and then we're going to be biased towards the initial sample for sure. So this is something we need. All parts of the initial sample have been changed, and I'll call those incidences. I have a picture to show you what I mean there. This is again the initial sample. And now all these node edge pairs, these are what I call incidences. So the question is, how many steps of the algorithm do you need to perform to for all these incidences to have had the opportunity to change somewhere? And this is not very rigorous theory. This is just for intuition. But let's see how many incidences we can change at maximum during every step of the hypershuffle algorithm. So I'm going to pick 2 edges. I did that, the blue and the orange one. We're going to take the union. Now we're going to repartition, and we're thinking about how do we repartition this in a way that we change as many incidences as we can. That's in this way, or an equivalent way. We can change 4 incidences at maximum. There's no way of repartitioning these sets in order to change more than these 4 incidences. And that has to do with the size of the smaller of the 2 edges, right? If the smallest edge is 2, then we can change 2 times 2, which is 4 incidences. If the smallest would be 3, we could change all 6. We can change 6 incidences. So this is an observation that we did. We can change 2 times the minimum degree of 2 edges. That many incidences we can change in every step. And for the other algorithm, exactly the same things hold. But now we don't look at the sizes of the edges to find out how many incidences we can change, but we look at the size of the incidence sets, which is actually the degrees of the nodes. So now we have this inequality. And from this, we can come up with the hypothesis that the hypershuffle algorithm is faster than the hypercurval algorithm if this quantity here is larger than this quantity down there. Right, so we did a bunch of experiments to verify this. I'm going to show the results in the middle figure, but let's look at what we had for every experiment. We got a figure like we have on the top left with these 2 lines. And in the middle, I'm going to plot 1 line per experiment, which is going to be the blue line minus the orange line. So it's going to be their difference. And if this line is positive, it means that the blue line exceeds the orange line, so that the blue algorithm is faster. If it's a negative line, then the orange line is faster than the blue line. So in practice, the positive lines have the hypercurveball algorithm being faster, and the negative lines have the hypershuffle faster. So, and every line is a different data set. So we have 25 data sets here, I believe. And roughly half of them have one algorithm which is faster, and for the other half, the other algorithm is faster. And now to check our hypothesis, we color the lines. So for every data set, we can check whether the inequality holds one way or the other way. And then if all the positive lines are red and the negative lines are blue, then our hypothesis seems to hold. And this is indeed the case. So for all the data sets that we checked, the hypothesis seems to be true, which is great. Because now, if you have a system that you want to randomize, you only need to check this inequality to know which of the algorithms is faster for you to use. So that's very convenient. But still, you don't know how many steps exactly you need to perform. So for that, we did another plot where we have the mixing time on the y-axis and some function on the x-axis, which is also including this expectation that we saw before. And then there seems to be some linear relationship, at least on the log-log scale, from which we can extrapolate and guess the mixing time kind of like this, which seems to be almost linear. So that's a convenient result. So now, if you have your system, you also know how many steps of the algorithm you would want to perform. Okay, so let's see if this if the new theory also holds for our specific little example. So we know the degrees of the hyperedges that we have involved, so we can compute these two quantities. These are the results. And from this, again, we can see that, well, the expectation with respect to edges exceeds the other one. So again, we learn that the first system is faster than the second one, which we already knew as well. So here the result also holds. Okay, so this is the third takeaway. We can tell which of the algorithms is going to be faster for your specific case if you give us the node and hyperedge degrees, and we can also give you some estimation of the mixing time. All right, now we're going to, this was the main content for my talk. Now I'm going to go back to the chemical reaction networks that I talked about in the beginning. So I want to compare my specific hypergraph with the random version. Of course, this is the directed version. I can't immediately use the algorithms that I just presented to you. So let me quickly show how those undirected algorithms also apply to the directed case. I won't go into a lot of detail, but it's a very intuitive translation, I would say. So we're going to start with the small initial sample again. And this is the hypershuffle algorithm. It's almost the same as the undirected case, but now we pick two hyperedges here. And we're going to consider the tails and the heads separately. So first we're going to partition the tails and then the heads. So these are the two edges. I first look at the tails, so only A, C, and D. And we repartition. And then the same for the heads. So I pick B, C, A here, and we repartition. This is one step of the algorithm, and then we obtain this new graph. And similarly for the hypercurveball algorithm, we pick two nodes. And now their incidences also have a direction. So we have out incidences and in incidences. We first look at the out incidences and we repartition, and then we look at the in incidences and we repartition. And we obtain this one. So it's the same strategy as before, and also the same theory that we presented before holds here as well. So we also know that these algorithms give us the uniform samples. Okay, so these ones we can apply to my initial hypergraph. And now, if we have such a null model, what we can do is we can measure each of those random hypergraphs. In this case, I'm going to look at a measure which you can compute for every node separately, gives a different value, and it looks at in how many reversible reactions a node participates. So here I'm going to sample 10,000 random versions of this hypergraph, and I'm going to measure each of those hypergraphs with this specific measure. And then we obtain a range of values for every node that they can take in the random case. It looks like this. So here on the x-axis, we see all the different nodes. And on the y-axis is this specific measure that I'm not going to go into too much detail. And then for every node, we see that there's some range of values that the random graphs seem to take. And now if we plot the specific data of this hypergraph, I did that here with the circles, you can tell that some of our measured data falls quite well into the random data, and some, which I colored red, don't. So these are measured values that probably are not due to randomness, but they tell us something about the underlying mechanism of this specific hypergraph. In this case, they might tell us something about the underlying chemistry. And this is still an ongoing work, so I can't tell you much more about it than this because we haven't analyzed it too much yet. But yeah, that was the main thing I wanted to tell you. So let's summarize. So I told you about how to sample hypergraphs with fixed degrees uniformly at random. I presented two algorithms. One is the hypershuffle algorithm, one is hypercurveball. We have some theoretical results that show that both algorithms work like we want them to. And we have some experimental results showing which one is the fastest algorithm, depending on your degree sequence. We could also give you some estimation of the mixing time for the specific algorithm. Ah, yes, this is the work that it's based on, and I'd be happy to collaborate if you have some cool ideas for future research. All right, that's it. Thank you.
Thanks a lot, Yanna, for this nice presentation. Everyone is clapping virtually. Um, Now we have some time for questions. So if you have any questions, either raise your hand, write in the chat, or just talk. I think that's yeah, up to you. Let's see if we have any questions. I have one, but Haley, please go.
So I don't know. I followed your talk really clearly. That was really interesting. Thank you so much. I don't know a ton about hypergraphs, and so I'm curious, what's the motivation for rejecting the shuffles that end up with a degenerate hyperedge?
Right. So for my specific use case, we do want the degenerate hyperedges because in chemical systems they make sense and they can be interpreted really well. But if you would, for example, analyze a social system where the hypergraph is undirected and the hyperedges are social interactions, then a degenerate hyperedge is a bit difficult to understand. And then you may not want to include those in your analysis. So that could be a reason to not include those. The same, you can apply a similar strategy if you, for example, don't want to have multi-edges or multi-hyperedges in your system. You can apply a similar algorithm, or if you don't want to have self loops, this all depends on your specific application and whether these structures make sense or not.
Would it be
Perfect. Thank you
similar
so much.
to having weighted edges? But maybe it's
Sorry, I missed the start of the question.
would it be similar to have not weighted edges but weighted nodes in each edge, something like that?
Yeah, you can interpret them as weights as well. Yes, you could.
But maybe
Yeah.
it's more complicated to represent it. I don't know.
Uh, well, I mean, I guess it's just a matter of interpreting, right? Um, maybe in a social setting, you could have weighted nodes in an edge, depending on how much someone is participating in your social activity. But,
Yeah, I was thinking something
yeah,
similar, yes.
yeah.
We have some questions from the chat that I'm gonna read.
Ah, oh,
So there is a question from Bunmi saying, first, thank you, it was a really cool paper, but they didn't get the mixing time derivation, if you can explain.
the mixing time derivative. Do they mean the intuition that I presented or the
I think how you derive the
experiments?
formula, like probably it's like the regression on data, no?
Mm,
For the mixing
yeah,
time, but I'm
this
not sure.
one, maybe. I guess this one. So we plotted, we performed the experiments
They,
for
they
this
say
bit.
they said before, yeah.
Um, oh wait. So this part probably.
Yes.
Yes, I see. Right. So again, this is just intuition to get a hypothesis. This is not theoretically sound. What is theoretically sound is these two observations about how many incidences we can change per step. So we can go back to the hypercircle, which is the example down here. So in a hypercircle, we pick two random hyperedges. They have some size, which is random. In this case, it's size 2 and 3. And now the maximum change that we can make towards the hypergraph that we are currently at is, in this case, if we change all the incidences in the smallest hyperedge, and we change them with the nodes from the largest hyperedge. So this is one example. There are different ways to do this. Obviously, this is usually this, or in the algorithm, this is all random, but here I'm looking at the extreme case. So what is the most change that we can make within one step? And that's done always twice the number of nodes in the smallest hyperedge. So that's what we see here as well. So here I put twice. This is the minimum degree of two hyperedges. And since we pick the hyperedges at random, we put an expectation there as well. And then for the hypercurveball, it's the same idea, but now we don't look at the hyperedges and their set and their size, but we look at the incidence sets and their size. And the sizes of the incidence sets are just the degrees of the nodes. So now we look at the minimum degree of two nodes times 2. And so this is the maximum number of instances that you can change per step. And now from here, there's no theory, but there's intuition that maybe the algorithm which can change the most incidences per step, maybe that's the algorithm that can also change, or that can mix the fastest. So that's how we came up with the hypothesis here, which we then experimentally verified. I hope that explains it a bit better.
How do you make it theoretically sound in principle?
Ooh,
Yeah.
this is a whole different field. Mixing time theory is a very big field, and it's very difficult in practice to so I haven't dived too much into this field because I know it's very difficult. That's why we only did the experimental part. I'm not exactly sure what kind of techniques people use to compute the mixing time.
Maybe connected to this before I go to the next question. Like now that you were explaining this, I was thinking, is this like you use the expected value, but is the distribution Gaussian of this minimum D1, D2?
The distribution depends on the degrees that you picked in the beginning. So it could be Gaussian, but it could be any distribution. This is a very general result that
Mhm.
we have. If you would, yeah, you could probably specify it and get a clearer result um, if you know the degree distribution. Yeah.
No, because I was thinking that, yeah, I would assume it's not in the sense that, yeah, if you have degrees that are from a real network and you have heavy tail distributions, then
Yeah.
I don't know, but probably also this could be not uh,
Yeah. Could be that
Gaussian.
maybe the node distribution is heavy tailed, but the edge distribution is not.
Yeah, I
Mm.
see.
Because, for example, in the chemical systems, you usually um, have a reaction from one to two nodes or two to one, but it doesn't get a lot bigger than that. So
I see.
there it might be Gaussian, yeah.
But it's still very interesting that this works. So it's really cool.
Yes. Yeah.
There is another question from Joel. Actually, several questions. So
Okay.
the first one is, have you tried combining the two algorithms, sampling a bit from one, from let's say the hypercurveball for some time, and then go to the hypershuffle for the other time? Have you tried
Hmm.
this?
I haven't tried, but I've thought about it. So um I would think that if you combine the two, then you would get some sort of line which would be in the middle. Um, so maybe if you don't know which of the two algorithms would be best for you, you can try to combine indeed. But if you do know which one is faster, then it's always better to only use that one. Given that you know that in theory your Markov chain is going to be have a uniform stationary distribution, right? So these theorems that I presented in the beginning, if you don't know, if you know for one of the two algorithms that the Markov chain has a stationary uniform distribution, but the other one you don't know, then this combining would be interesting because then you know for sure that you're gonna converge to some uniform distribution, which you want. So that could be a reason to combine. Otherwise, I think especially given our hypothesis that seems to be experimentally verified, it seems to be the best to just pick the fastest one for your case.
And yeah, makes sense to me. The second question is, instead, can you parallelize by partitioning the graph, sampling on parallel on each partition and then repartition, or combine with the MCMC on the partitions?
Oh, that's an interesting question. I haven't thought about that. Um, I mean, you could. I'm now think I'm trying to think of whether the theory would still hold. I'm trying to think whether you're still going to arrive at the uniform sample. Because one of the problems that I'm seeing is that if you partition your graph and you're gonna mix both partitions that they cannot mix together. So there are gonna be some graphs that you will not be able to reach in that way. Um, so I'm seeing some problems there, but maybe if you partition, yeah, if you partition at random and maybe a few times, it could work. Yeah, it would maybe be a lot faster. That's interesting. I haven't looked into it more than this, no, but it's a cool idea. I don't know, is this being done by with other Markov chain algorithms? I haven't read about it, but if it exists, I would be happy to hear.
Not that I know, but if anyone has any ideas, let us know. And yeah, my question was because you have a dependence on the degree in both cases, but can you also see a clear dependence on the number of nodes and edges in any way? I guess, I mean, the degree depends on that indirectly, right?
Yeah,
Is
yeah,
it,
that's true.
yeah, is it easy
So you
to change between the two? Like, I guess no, but
to change between the number of nodes and their degrees.
yeah, so find a way of, I don't know, like you know how many nodes and edges, hyper edges you have, and know how is this related to this.
So in this slide where I kind of showed how we can estimate the mixing time, we have this function here at the
Yeah.
bottom. And here we do have the number of edges times their average degree. So basically this function, the top part tells us how many incidences we have, how big your system is, and then the bottom part tells us how many of those, how many instances we can change per step. So this is where the size of the hypergraph also appears. And yeah, the larger the hypergraph is, the larger your mixing time is going to be. Yeah,
Okay.
but it seems to be somehow almost linearly related. So that's interesting.
Yeah, that's really nice.
Yeah.
And yeah, I agree with Annie that said that you explained really complex ideas in a really clear and simple way. So
Happy
thanks a
to
lot
hear.
for this talk. It was really nice. And do we have any other questions? Seems no. So
Okay.
thanks a lot for this. I'm gonna